All right, how's it going, everybody? We are here on Friday, February 5th, and today we are going to talk about section 6.7, the graphs of tangent, secant, cosecant, and cotangent. Just a little bit, I guess I'm going to point above my head right here. Remember that this week we covered two sections, 6.7 and 6.8, but we did them in reverse order. That's because last week we started with 6.6, which is our introduction to sine and cosine. Then I went out of order and did 6.8, which was more things about sine and cosine. Today, now we're going to look at our less important graphs of tangent, secant, cosecant, cotangent. When I say less important, I do not mean not important. I mean less important. Sine and cosine graphs and their transformations are certainly the most important graphs that we want to come away from this class with. But knowing some basic things about these graphs as well is going to be pretty important here. We aren't going to go into as much depth with all of these graphs here. All the difficult graphical questions I'm going to ask you are always going to be related to sine and cosine, but I do expect us to have some like basic comprehension of our other four graphs that are out here. Um, so let's kind of get going here. And I mean, really like kind of notice that like we spent two sections on two of our graphs. Now we're going to spend one section on four of our graphs. So I think the relative importance is there. That says to me our sine and cosine graphs are approximately four times as important to me as our other four graphs are right here. And I think that's a pretty, I think we're distributing our time appropriately in this way right here. So, as it's been the case all semester, once we know what we need to know about sine, cosine, and tangent, that will give us everything we need to know about secant, cosecant, and cotangent. So all the information that we want to acquire today is just going to keep on saying like, well, I don't know, what happens with sine? What happens with cosine? What happens with tangent? So what we want to do today is establish tangent first, and then use sine, cosine, tangent knowledge to get our secant, cosecant, cotangent knowledge. It's what we did before we were starting to graph these functions. It's what we're going to do now. The other thing that we know is that all six of our trig functions are periodic. And what that means to us is all we really need to be able to do is to be able to graph one period of the function, and then we can repeat that any number of periods to the left and to the right out there, right? So this is saying, this isn't like we're drawing an infinitely wide graph necessarily. It's that we need to come up with one sliver that then repeats over and over to the left and to the right. So the one that we want to cover first is going to be tangent. And what I want to start with today is actually not actually graphing the tangent function, but coming back to the unit circle. There's a thing that I said that I was going to bring up, and then I probably should have brought it up last week. And this is sort of like I half forgot, but here's going to be a great place for me to flop in this knowledge right here is this. What I want to know is how could we visualize what the length of the tangent of theta is going to be? Some of the things that we saw that's kind of weird about tangent, that's different than sine and cosine, is that sine and cosine always outputs values between -1 and 1. They're always stuck in that range, right? And that's because the width on the unit circle goes from -1 to 1, that's cosine. The height on the unit circle goes from -1 to 1, that's sine. What I want to know is how could we visualize the length of the, right? We have literal lines that we can draw that say this is the cosine length, this is the sine length. Where's the line that we could draw that'll give us the tangent length right here? So what I actually want to do is come back to our unit circle for a little bonus like visualization that I kind of maybe should have done before, but that's fine. Now, at least we're getting it right now. It's going to help us draw a graph of the tangent function. So what I want to draw right here is I'm going to draw three total unit circles right here to kind of show us where we're at right here. So not my worst circle. So on the unit circle, and I'm gonna try and draw the same angle on all three of these guys right here. Something like a 60-degree angle, something like that. It's not necessarily 60 degrees, it's just some general angle. But what I know is I can draw this little right triangle right here, where the lengths on this triangle, we are just saying if this is any old point x comma y, then this length is x, this height is y, and because this is the unit circle, that radius right there, the hypotenuse, is 1, right? This is our most generic angle that I can draw on the unit circle, right? This is without us having actual knowledge of our trig functions, right? Now and by the way, there's our angle theta sitting down there in the corner, right? Now I ask questions like, what's the sine of theta? And if we look at this angle or triangle that we've drawn right here, the sine of theta, sine is opposite over hypotenuse, that's y over 1. Oh, well, that's just y. Y is the sine of theta. That length y is literally the length sine of theta. Very, very similarly, I can ask what's cosine of theta, and we look over here and say cosine is adjacent over hypotenuse. Well, that's just x over 1. That's just x. That length x literally is the length cosine. Right, so what I'm going to do now is I'm going to draw, I'm going to do myself a favor and draw the circle first because I've learned my lesson. So now I'm going to draw my new unit circle. You know, my circles are a lot better when I go slow and draw them before the axes here. So now I'm going to draw kind of the same thing, right? Here's my same point, but we're now recognizing that this literally is the length cos x, or oops, nope, don't want to say cos x, I want to say cos theta. That's kind of important right here. I'm talking less about the algebraic function y equals cosine of x, and a little bit more about the ratio, that's associated with that cosine value right there. So here's what I'm seeing. So now what I'm seeing here is that we could literally just label those legs right there. The length is cosine, the height is sine. And since it's the unit circle, that hypotenuse is always going from the center of the circle to the edge. So its length is always going to be 1. So here's what I'm going to draw now for my, I'm going to draw this one big. Ooh, man, drawing big circles is hard. All right, so here's what I now want to do. All right, so same location right there. What I'm going to do is I'm going to label this the same way. That's cosine of theta, that's sine of theta, and that's 1. But here's what I'm going to do, because I want to help myself visualize what this tangent length is going to be. What I'm going to do is I am going to extend this radius right here, right? So we've got our angle right here of theta, and it's suggesting to us to draw the terminal side of the angle as this radius line right here. And what I'm going to do is I'm going to extend this line through here. And what I'm going to also do is I'm going to draw a vertical line that's starting right here at the edge of the circle and is going to go vertically upwards until it touches this thing right here. Right? So what I've done here is I have made a second right triangle, the one that's got the purple border, and what you should notice is that this small right triangle on the inside is similar. When I say similar, I mean like the formal geometry sense, meaning has all the same angles as this large right triangle on the outside right here. So let's do a quick little bit of geometry right here and relate these two triangles. So the two triangles that I just drew are these two guys right here. There's one triangle that has theta in the corner, has cosine as the width, has sine as the height, and has 1 as the hypotenuse. The other triangle that I just drew is the one that's larger, that has a width of, well, let's judge the width here in a second. And then I'll go back and to make sure that we see it, these are the same right here. Great. So there's my large triangle right here. Now notice in this large triangle, this interior angle right there for theta is the exact same. And therefore, it must be that these are similar triangles because they both have a right angle in the bottom right corner. They both have an angle of theta in the bottom left. So the upper angle has to be matching, whatever it is. It's 90 minus theta, right? Now, what are any of these lengths? Do I know any of these lengths out here? And my question is going to be, what is this length y right there? That's my question. I want to know what height that is right there. Well, the only length that I actually know on this thing, because I don't know this hypotenuse length, and I don't know this vertical length, but notice that with this new triangle right here, that is just 1 radius on the bottom, and we've decided that our radius is going to be 1. Right? So, since these are similar triangles, that means that the ratios of their leg lengths are always going to be the same. If you pick any sides and make any ratio of side lengths, it's going to match between triangles right here. So what that says to me is I can do things like say the ratio of their 2 legs of the small triangle should be the exact ratio as the ratio of the 2 legs of the large triangle because they share all the same angles. So similar ratios match. I'm going to build a ratio here. My ratio that I'm going to build is going to be the sine, this leg, divided by the width leg, sine over cosine. Which legs does that correspond with over here? Well, this one that I'm calling y, I'm calling it y because it's a vertical distance right there, over 1. Well, look what this simplifies down to. So what this is saying to me right here is that this length that's right here, this literally is the length of tangent right here. When you evaluate tan theta, what we're seeing is it's exactly this height of if you were to extend your angle through the unit circle, wherever it intersects this vertical line that's at the edges of the circle right there. So there's a vertical line at x equals 1 and a vertical line at x equals -1. Wherever our ray intersects that triangle, the height from the x-axis to that intersection point is going to be exactly the length of tangent right there. So this is a good visualization that helps us see things like the fact that tangent can be bigger than 1. I know that this height right here is 1 because it's a radius 1 circle. As I've drawn it, it looks like tangent is larger. And in fact, we know that at 60 degrees, tangent takes on the value of the square root of 3. That's more than 1, right? And so this is going to be kind of helpful for us with our visualization. One of the things that you should be imagining now also is this. As an angle opens up from 0, we're always able to form that triangle that's in whatever that is, pink or purple right there, magenta. But notice that that triangle is not going to be possible to draw when we're at 90 degrees. We know that the tangent function is missing a piece of its domain at 90 degrees right there because sine over cosine is 0 here. This causes the division by 0 error when we talk about tangent right here. And then we're going to pass into our negative tangent values over here because sine is positive, but cosine is negative right here. So this is going to be like a helpful visualization of the unit circle for tangent that I think is going to be helpful for us in actually graphing the tangent function now. All right. So this is your helpful thing for tangent. Where tangent is visualized on the unit circles, it's not within the unit circle like sine and cosine are. It's that you can take, so my like smaller drawing right here is, just imagine there being these two lines right here, and any angle that you draw, you can extend it right there. So if that's theta, then this height right there would be our tangent of theta right there. That height that we're seeing on the outside of the circle of the vertical leg of a triangle, if that ray were extended to that vertical line out there. And this is a good visualization to kind of help remind you of what types of values should you be expecting for tangent. The only thing that's a little bit tough with this one is that, for example, right here, we're going to get a positive value for tangent because sine is positive and cosine is positive, and tangent sine over cosine. For this guy over here, we're going to get a negative value for tangent because the sine is positive, but the cosine is negative right there. So it's hard for us to interpret the sine, the positive negative of it by this visualization, but this should help you with your magnitudes right here for your visualization. So let's use this information here to kind of describe some properties that we just saw right here. Right? So period, domain, and range of the tangent function, these are all things that we've already talked about, but what I want to say is from the unit circle, can we see these things? So restating some important things right here. So one, how much angle do I need to go through before it repeats? Well, I'm noticing that tangent, as I open up right here, is going to pass through all positive numbers. This is a tangent to 0 because sine is 0 and it's sine over cosine. So our tangent value is 0. It's going to increase, increase, increase. At 45 degrees, I know that tangent is 1. And notice, based on this picture, I see that tangent's just going to get like infinitely tall. When we make this like 89-degree angle, this line is going to go up a real long way before it finally intersects that vertical line right there. I think we did this in our calculator last video and saw that we're getting an answer of like 57 or something like that. And that's only at 89 degrees. Now we go to 89.9 degrees, we're like almost vertical. It's going to go up so freaking high up there. And so the closer and closer our angle gets to 90, the closer and closer that tangent height gets to being infinitely high up there, right? But then as soon as we're at 90 degrees, I can no longer make that connection to a triangle over there. There is no more measurable height for tangent. So at 90 degrees, we lose the tangent measurement right there. We don't have it, right? So we got all positive numbers from 0 to 90. Now, as soon as we get on the other side, 91 degrees, we're going to get a very large negative number because our cosine values are now negative. So sine over cosine will give us a negative. So we're going to get all those large negatives all the way down to the negatives that are small down to 0. So we just traverse through all positive numbers, then through all negative numbers. Once we go into the third quadrant, we're just hitting our positive numbers again because in the third quadrant, sine and cosine are both negative. And so when you take the ratio, you get a positive number. So in the bottom half of the unit circle, we get all positives again. In the third quadrant, I can't do my R math. And then in the fourth quadrant, we get all negatives again. So these repeat every 1 pi, not every 2 pi. We don't have to take a full lap around the circle to see every possible value and then to experience them again in the same order. We only have to go halfway around the circle for that, right? So we can see from this that our period is pi, and I'm going to put underneath it importantly, not 2 pi. Right? The period of tangent is different than that of sine and cosine. Recognize that sine measuring height, right? Sine is 0 right here. Sine is going to go from 0 through the positives to get to just 1, so it doesn't even get off to any numbers bigger than 1. And notice that then we just repeat all those numbers again. Then sine goes from 1 to 0. So we just got duplicates right there. Now to get our negatives, we have to go through all the negatives, 0 to negative 1, and then negative 1 to 0 again. So we duplicate up all the negatives as well, but now we're back to the beginning for sine. So that took a full rotation of 2 pi for us to get back to starting the process over again. A little bit different right there. The other thing that we're seeing is what's the domain of tangent here. We're asking what values are we allowed to plug in to tangent. And the reason I scrolled up a little bit is because this is all we really want to remember. Tangent is sine over cosine. So that means our domain, the values that we're allowed to plug in for theta, are just the values that make us not divide by 0. When is cosine 0? Cosine is measuring width, and we have no width at 90 and at 270, also known as pi halves and at 3 pi halves. And then again at 5 pi halves, 7 pi halves, 9 pi halves, all those odd pi half powers out there. So I'm going to say here, those are where we divide by 0. So x cannot be equal to pi halves plus pi k, right? Keep on adding another pi rotations from here. We go vertical, horizontal, vertical, horizontal. Those are all the places where we can't have a tangent value. Let me just say, can't have cos x equal to 0 with tan x equals sine x over cos x. Finally, what's the range of the tangent function? That's all possible outputs that we get from the function. That is all the heights that we're ever going to see. And notice from our picture here, we can see that purple line, or that pink, okay, I'm just going to call it magenta since that's probably its actual color, starts at 0. We're going to experience all possible positive numbers in 0 to 90. Then we're going to experience all possible negative numbers from 90 to 180 out there, because it's going to be like an infinitely long line up there when we're at like 89.999 degrees. And I mean, do that in your calculator. I'm just going to do it right now. In my calculator, the tangent of 89.999 degrees, I'm going to make sure I'm in degree mode right here. The tangent of 89.999 is 57,295, right? So we get out larger and larger numbers as we get closer and closer to that vertical right there, right? But both of these guys right here that are barely off of vertical, they're going to have massive tangent values out there. And you can get as big of a number as you want by getting as close as you want to being perfectly vertical right there. So that's basically saying to me, all positive numbers and all negative numbers are going to get got by tangent. So that says to me, everything's possible. We can get 0. That one's possible. 0 is always one that you should like check, separately whenever you're asking questions like these. So this is everything. And remember, this is different than sine and cosine. Notice that because sine and cosine are trapped inside the unit circle as lengths, it's not possible for them to get to be bigger than 1 or negative 1, depending on direction. So these sine and cosine are stuck in the negative 1 to 1. Remember the difference here too. Brackets mean we're including that value. Parentheses mean you disclude the value, exclude the value. Infinity is not a number, so it always gets parentheses right there. So what we're saying here, and I mean, like, notice, like, none of these features match up with sine and cosine. Sine and cosine have their full domain. You can plug in anything. Not true of tangent. Sine and cosine have a period of 2 pi. Tangent has a period of pi. Sine and cosine have a domain, or have a range of negative 1 to 1. It's what you get out from it. That's tangent can get out anything right there. So tangent has a lot of doesn't have a lot in common directly with sine and cosine, even though it's made by sine divided by cosine. A lot of its important properties don't quite match up. So what that means to me is, even though tangent, I'm going to get all my information from knowing it's sine over cosine, as far as the graph of tangent goes, I don't think it's going to have graphically much in common with the graphs of sine and cosine. Like, sine and cosine live right here between negative 1 and 1. Tangent's going to go off forever. Sine and cosine, you can plug in any number you want. Tangent has an infinite number of numbers, the pi halves plus pi k, where there is no sensible input. We'd be dividing by 0, giving us just a computation error there. So there's holes in that thing right there. The tangent graph is going to repeat every 1 pi, not every 2 pi. A bunch of stuff like that, right? So to do this then, I think we need to return to our plot some points technique right here, which is always lame, so let's do the least of it that we can possibly do. So my question for you then is, what are the easiest values that we know for tangent? I'm remembering that tangent of x Always remember that tangent, sine over cosine. It's like always a place to go back to. And so I'm thinking to myself, what about tangent of 0? Well, at 0 degrees, or 0 radians, you're getting the sine of 0 over the cosine of 0. Sine of 0 says, what's the height of this point? It's 0. We haven't gone up or down at all. What's the width of this point? It's 1. We've gone a full 1 unit from the radius to the right here. So it looks like tangent of 0 is 0. So that says to me the point 0, 0 is on the graph right there, right? That's always a nice point to have on a graph, right? The other nice value that I know that I get out from tangent, and this is something you should have learned from your unit circle by now, is that our tangent of pi fourths, or 45 degrees, is right where sine and cosine are equal to each other. And if our sine and cosine are equal, then we should just be getting out 1. And the other thing that I know is that tangent of, for example, if we were to go in the other pi fourths direction right there, if we did negative pi fourths, then here we're still going to get same lengths, except the downward component is negative. So we're going to get a positive length and an equal negative length. And the fact they match gives us 1. The fact that one of them is negative negates it right there. And so we're going to get negative 1. So this says to me, I think the 3 easiest values to think about for tangent right here are the x values at 0, at pi fourths, and at negative pi fourths. We also know that tangent has a much larger range than sine and cosine, meaning the output span is much broader. Sine and cosine, you're only ever going to get out stuff between negative 1 and 1, but tangent, you can literally get out any number. It's a way broader variety of values that are possible for outputs. We don't usually see them until we're like really close to these large values up here, or excuse me, these values that are very close to 90 or very close to 270 down here, but it's possible to get out literally any real number. So my question is, what angles produce such large values? And we know it's going to be these ones that are very near to 90, because that's where this line is going to go up for a real long time before it intersects that vertical line that's out there. Right? So we're seeing things like angles very close to pi halves, that's our vertical upwards, and 3 pi halves, that's our vertical downwards, produce very large tangent values. And all I'm really saying here is once we get close to this, that says to me, for example, we're looking at things like 89 degrees, comma, large number. Right? I'm not trying to get too technical with this right here. I'm just saying those are the types of values that I'm expecting to get a really, really, really big number, tending off towards infinitely large as that 89 gets even closer to 90 right there. And same on the other side of 90. So I think this is kind of enough information for us to get a graph going. So let's do this. And actually, hold on. I want to say one more thing here real quick. What is a typical thing to do when trying to graph our first period of this is that I know that where I'm going to have my domain end is going to be at pi halves, right? So I'm going to go from 0 up to pi halves, but when I get here, there's like a gap in my tangent value. There's no way to define tangent at pi halves. You're dividing by 0. So what we're going to do to draw our first period of this is we're going to look from 0 to pi halves, but rather than cross over our domain hole, we're instead going to also look in the other direction because our other domain hole is down here, right? So I'm picturing to myself, I want to graph negative pi halves to positive pi halves as my one full period. This gets me all my positive outputs. This gives me all my negative outputs. And we don't cross over one of those missing places of the domain in this span right here. Our 2 edges are a missing domain spot at 90 and a missing domain spot at 270 right there. So that's what I want to graph first. So I've got 3 points, and I've got a conceptual point or direction associated with these guys right here. And I think that's enough to graph this thing. So let's say that this is our graph of y equals tan x. And there's a bunch of features that I want to identify here. All this information on this page I'm going to use to help me draw my graph. So first things first, draw the easy points. 0, 0, pi fourths 1, negative pi fourths negative 1. So those are my first 3 points. 0, 0, pi fourths 1, negative pi fourths negative 1. I know those. The next thing that I know is that if I get really, really, really close to pi halves, I'm going to get massive values out here. So I'm seeing things like very close to pi halves, but not at pi halves If you try to plug in pi halves, you're dividing by 0. There is no value that we get on this vertical line here. But stuff close to it should be giving us very large positive numbers. So that's sort of my concept point right there, right? There's my 89 degrees gives us something huge, right? Similarly, down here, as we get very close to negative pi halves, that's going to be another one where we're going to get a really massive length down there. Right? Now, the other thing that I know about this is that at pi halves and at negative pi halves, those literally aren't even in the domain. You cannot plug pi halves into tangent. It's not like you're getting 0. You're getting 1 divided by 0, and that's not a number. It does not exist. There is no value. But I do know that these values are going to get really, really close to that line, and so I believe that most of us are familiar with the concept of an asymptote, a line that we get infinitely close to, but that we never touch. That's what we're going to experience here at this pi halves right here, and at negative pi halves. Right? And this is going to give us our general shape of our graph. Knowing that we're not going to cross over this line, things just keep on going down here. Things are just going to keep on going up there. So we're getting for our tangent something that's going to look a little like this. So there, notice that this interval has a width of 1 pi, because we went from negative pi halves to positive pi halves. So this is 1 full period. And so what I know is that it must be the case that this thing right here is just being copied and pasted to the left and to the right forever, because this is a periodic function. It's exactly equal when you just go 1 period further. So that says to me, I can go to my next location that I know that I have an asymptote. And by the way, we have these domain issues at pi halves plus pi k. Well, if I let k be 1, then pi halves plus pi is 3 pi halves. Or pi halves minus pi is negative 1 pi half. We already drew that one. Subtract another pi, we get negative 3 pi halves. So we see that we're going to keep on getting these asymptotes here at these odd multiples of pi over 2, I guess I should say. We can see here that at the location pi, since this has a period of 1 pi, I should be able to just shift this graph by pi and get the exact same stuff. So 0 minus pi is going to bring me to here. Notice that at negative pi, we're back around to our angle that's pointing directly to the left right here. This has no height, and so we're getting sine over cosine is 0 over negative 1 in this case right there. At negative 3 pi fourths, that's going to be pointing down like this guy here. Notice that negative over negative for sine over cosine is positive, so that's why I'm getting positive 1. And at negative 5 pi fourths, that is at 1, 2, 3, 4. Oh, excuse me, I went in the wrong direction. Negative 5 pi fourths would be 1, 2, 3, 4, negative 5 pi fourths right here. We have a negative cosine, but a positive sine, so we will get a negative 1 at that location as well. And that just says to me that like our values are like agreeing with what we previously did right here, right? So we are seeing what we expected, which is this repetition right here. And again, obviously this looks nothing even remotely like our sine and cosine graphs here. Nothing even remotely like our sine and cosine graphs. But all of our knowledge kind of still came from the unit circle and thinking about always the fact, man, it's never going to stop being a thing that when you think about tangent, you should be saying to yourself, okay, well, I know it's sine over cosine. It's just always, 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 always a useful place to be. And it's going to be even more the case when we get out there to chapter 7 stuff out there. So I kind of can visualize for myself that there should be some other parts to this graph. Like kind of, here's my next stuff that we would see if we kept on going further out there. But this tangent graph is going to have vertical asymptotes at some locations here. Oh, wait a second. Oh, okay, never mind. Let's go ahead and list all this stuff right now. So now we can visually see on a graph some of these things. And by the way, let's just pop over to Desmos super quick so that I can show you guys what a not crappy graph looks like for this one. Uh-oh, I didn't bring up my Desmos. Yeah, I did. There we go. And if you just go to Desmos, y equals tangent of x, and they're showing us exactly that same type of stuff right here. We can do things like x equals pi halves. There's that first asymptote right there. X equals 3 pi halves. X equals negative pi halves. Stuff like that. You can see these vertical bars right here. Maybe better seen as black dashed, or let's make them dotted lines, something like that. Stuff like that. We can see these asymptotes where it doesn't matter how far down you go, we never actually get to the line, and it sort of looks like we do, but like you can just zoom in and see like, oh, nope, we never actually got there. I can see the gap out there. So these asymptotes are lines. All asymptotes are lines where in the long run you get infinitely close to it. It's typical to never ever intersect a tangent line, at least in our long-term behavior. You'll learn in algebra class that we do occasionally cross over tangent lines. I'm talking about asymptotes. We do occasionally intersect asymptotes, but in the long-term behavior, we do not. In the long-term behavior, we tend towards them, but never actually like arrive at them here. So, switching back over here, let's go ahead and not look at my chunky looking graph right there. But again, use this graph to confirm some features that we're seeing right here. So graphically, what I can see is that there's no x values that actually have outputs at these odd multiples of pi halves right here. So our domain, I'm again going to list as what values don't we plug in? Remember that this is all inputs. And here I'm basically saying all inputs are okay as long as you're not doing the input of pi halves and any of the multiples of pi beyond that. What's our range? Our range is our outputs. We can see what the range is from the graph because I can visually see that this graph goes up forever and it goes down forever and it gets everything in between. So that's why I'm saying our range is all the numbers between negative infinity and positive infinity. The next question is, what symmetry does our graph have? And you should notice here that if we flip this graph horizontally, we don't land on the same place, right? We would get one like the opposite direction right here. Similarly, if we flip it vertically, actually we'd get the exact same thing as if we flipped it horizontally, right? It would just be that this top part would now be on the bottom and the bottom would be on the top. However, I can notice that if I were to take this thing and grab it and rotationally rotate it by 180 degrees, it would land right back on itself again. And actually, it's the same thing as doing both a horizontal flip and a vertical flip. If you did both of those flips, then we would land back on ourselves. This is what we refer to as odd symmetry. And as I said, by taking the, let me say tangent of x, you can do both a vertical flip and a horizontal flip, and you'll land back on yourself again. And you should take a moment and convince yourself of that right here. Or maybe we can go look at this guy in Desmos over here. If I were to take this tangent function right here, and first I do a vertical flip. I know this is a vertical flip because vertical is top and bottom. That's y stuff. Y stuff is output stuff. I'm going to make the adjustment outside of the function. So when I negate it, it did a vertical flipping right there. Mirrored it top to bottom, right? I feel like when I look at this, it feels like it looks like a left-right flip right here, but stop for a moment and convince yourself that like this bottom arc right here, if you flip it over the x-axis, it becomes the upper arc that we have right there, right? And then notice that if I also negate the inside, we're back at the original tangent function right there, right? And also noticing that the negative on the outside in this case is the same as the negative on the inside in this case right here because we have odd symmetry. That's a special property, definitely not true of all functions. Here it's especially true of tangent and of sine, it turns out. So again, play with this stuff in Desmos. Oh my gosh, you just get unlimited graphs for free that are such high quality that it takes zero effort on your part. This is the place you should be learning this stuff. We can visually see the period of the graph that we drew right here. Our period is 1 pi, not 2 pi. It is 1 pi for our period right here. We repeat the entire graph every width of 1 pi. Where do we hit the x-axis? Well, we know that when do we get outputs of 0? Since it's sine over cosine, the fraction needs to be 0 in the numerator. So it's wherever sine is equal to 0. And that's going to be at 0, at pi, at 2 pi, 3 pi, 4 pi, 5 pi. Those are all the locations. We can see it right here. 0, pi, negative pi, stuff like that. So our x-intercepts here are at x equals, and I'll call this pi times k. It's all of our integer multiples of pi. 0 pi, 1 pi, 2 pi, negative 5 pi, 14 pi, negative 37 pi. Um, so we should say here tan x equals 0 equals sine x over cos x. True, we need sine x to be equal to 0. So all the places where sine is equal to 0 will result in 0 over something for tangent, giving 0. Right? And finally, where are we experiencing these asymptotes? Well, it's the exact same places that we have these domain issues right here. But in this case, since I'm saying where do we have asymptotes, I'll say it's at the locations x equals pi halves plus pi k. Notice here I'm not putting a slash through the equal sign. This slash means these are all the x values that are not members of the domain. Oh my goodness, oh my goodness. I forgot to switch over right here. Hold. Here we are back here. Okay, so let me say a few more words right here. So with the symmetry, let me back up a couple slots right here to where I was talking without being on the screen. Odd symmetry. We can see from this graph, if we rotate by 180, we land back on ourselves. That's our odd symmetry. That's also associated with both a vertical and a horizontal flip will land you back on yourself again. Our period, we can visually see, it's 1 pi wide. It's the width of each of our repetitions. Our x-intercepts are always going to occur when sine is 0, because since tangent is sine over cosine, and we want a output, a height of 0, a fraction is always equal to 0 when the numerator is equal to 0. And so anywhere where sine of x is equal to 0 is also where tangent of x is equal to 0 right here. Those are our x-intercepts, where the height at the output is 0. Finally, our asymptotes are exactly the places where we were missing chunks of our domain, right? The only distinction that I want to make right here is that the domain is what are the acceptable inputs. So I'm saying it's everything except for x equals pi halves plus pi k, which is why I put the slash through this. This is saying it's all the x values that are not equal to pi halves plus pi k, where k is an integer. On the other hand, the asymptotes, I'm saying where do we have asymptotes? We do have them at x equals pi halves plus pi k. So these two pieces of information are identical. Just the way I express them is one with a not equal to and one with an equal to, because here I'm saying these are the terms that are not in the domain because they are asymptotes, right? So it's sort of like a verbal negative versus a verbal positive right there. Cool. So we've got all these features here based on that graph. The other good news for us is that all the transformations that we did with all of our sine and cosine stuff are all going to be the exact same types of transformations that we're going to get associated with our tangent. So let's go ahead and just do some quick ones right here. Tangent of x plus 2. How do I know what transformation this is going to do? Well, this plus 2 is outside of the function, so I know this is going to affect my outputs, my y values, so this should be a vertical adjustment. I know that I'm just straight up adding 2 to all of what used to be my original y values, so this should just be a vertical shift up by 2. And so graphing that is going to be hard. Graphing all of these is generally pretty hard. Hey, that wasn't that bad right there. 2. It's really the sine and cosine ones, man. I can see those from a glance a mile away exactly what properties they have. Much harder with this guy right here. So I think my most important thing is I've got that point at a height of 2 instead of at a height of 0, where we're kind of crossing over right there. Hard, but we can certainly give this verbally right here, a vertical shift up by 2, right? That's changing our midline, but the midline has a weird definition with tangent, you know? Y equals negative tangent of x plus pi fourths. Well, there's two things that I see that we're adjusting. What does the negative do, and what does the plus pi fourths do? Well, this negative is outside of the tangent function, so I know it's affecting our outputs, which are our y values. So this should be a vertical adjustment. This is going to say, take all of your outputs that were positive and make them negative, and take all your outputs that were negative, and since they're being multiplied by a negative, they're now positive. So this should be a vertical reflection. And what does the plus pi fourths do here? Well, we know that this is in our phase shift location right there, but even if you forget that, you shouldn't need that. Our more generic way to remember this is that this plus pi fourths right here, this is inside of the tangent function, so this is affecting our inputs. That's our x values. This is a horizontal adjustment that we're making. This is like me saying you're going to go to the grocery store and somebody's going to hand you $5. Therefore, your contribution, X, can get away with being $5 fewer than it used to need to be before for you to get the same amount of groceries out of that, right? So that plus pi fourths, remember that all of our input adjustments are the opposite of our intuition. So traditionally, I would think plus means go to the right. But here we are compensating for the fact that the plus 4 goes to the right by us going to the left. It's a compensation thing right there. So this is a shift left by pi fourths. So I know that it used to be the case that a pi fourths is where we were getting to the height of 1 on our graph, right? Tangent of pi fourths was 1. Well, now if I were to plug in pi fourths, I would get pi halves, which is our missing domain. Now if I plug in 0, I should get out 1. So I'm shifting the whole graph to the left by pi fourths. So notice that my two vertical asymptotes are no longer perfectly centered around the y-axis. They're now offset a little bit right here. And it should be that at negative pi fourths, I'm just going to mark 2 points on this graph right here. That should be at the point negative pi fourths 0. Because if you plug in negative pi fourths for x, negative pi fourths, and positive pi, oh my gosh, I drew my graph backwards here. I forgot about our other component here. At this point, I better just get rid of all that. My graph was good right there, except I forgot that negative that's sitting up front. I didn't do my vertical reflection. So notice, by the way, though, that we can still play this game. Even though the asymptotes aren't actually a component of the graph, they're just more of like a visual like border. You can shift those too, and that's really, really helpful for me. So I start this by shifting my asymptotes left by pi fourths. Now I'm going to handle that vertical reflection component, so I should be getting a graph that's going to do something like this right there. And notice that I vertically flipped this thing, right? And so now we have it's in a sense oriented in the other direction right there, which makes it, for some reason, way harder for me to draw well. So let me go ahead and label these two very important points right here. Now I can see that if I were to plug in negative pi fourths into this guy, I should get out 0. And that's because negative pi fourths, positive pi fourths make 0, and tangent of 0 is 0 because sine of 0 is 0. This point right here should be at the location. It looks like its x value is 0, and I know that if I plug in 0 for x, then I'm getting the negative tangent of pi fourths. Tangent of pi fourths is 1, and I'm going to take the negative of that, and I'm going to get negative 1. So by the way, this will be a thing where when I ask you to draw some of these guys, I might just say to you things like, clearly identify at least 3 points on your graph that aren't all like the exact same point, meaning you can't just pick like the x-intercept, and x-intercept or something like that. And so that would be maybe your good axis point. Or maybe I'll say something like, identify every single point that touches the x or y axis specifically, like I just did right there. Something like that, just to help me know that you know where these locations are actually occurring. Finally, right here, we can see this tangent of 2x. We want to recognize that multiplying by 2 is happening inside the tangent function. So this is affecting our inputs. Inputs are x values. X values is horizontal stuff. So I know this is a horizontal adjustment. This multiplying by 2 is saying things to me like, if you, again, back to our grocery store analogy, this is saying you are responsible for bringing X dollars to the grocery store. It looks like somebody's going to double your money on the way in. So that means you can get away with contributing only half as much. That's going to make our graph half as wide as it used to be. Right? So now I'm going to be getting that this is a vertical or a horizontal compression by a factor of 2. We're only getting 1/2 of the width of a period as we used to. So horizontal compression. By a factor of 2. Why are you graying? What's your deal right there? Tangent 2x, calm down. Jeez, a gray box right there drives me nuts. Our period is now It used to be pi. It's now pi over 2, right? It's only half as wide as it used to be. So now our graph is going to be, same, otherwise the same shape out there. But if before I had my asymptotes at pi halves and negative pi halves, those are now half as far away. They're at pi fourths and negative pi fourths. This gets real hard to draw well. Vertical asymptote at x equals pi fourths now instead of at pi halves right there, because we've squashed this thing in by a factor of 2 right there. Right? So all these transformations are still, and by the way, that should be like at the origin right there. That's not, I'll just make a big dot so it doesn't look too weird right there. And again, play with these things in Desmos. If you don't like the graphs that I just drew, go to Desmos and graph these things. Make sure that you understand how you could verbally describe each of these things. I will ask you to verbally tell me what transformation is happening relative to a function here. So expect to have to do that. So we now have our tangent graph. We've seen the transformations we can make to the tangent graph. Let's go ahead and hit up our other 3 graphs. Right? Now, we know is that our remaining 3 functions, tangent, secant, cosecant, they're going to have a ton in common with, sine, cosine, and tangent, right? So we just did tangent, so let's talk cotangent next. Let's talk about what we think they're going to have in common and not have in common, and then let's just have Desmos help us with these. I will also say we've kind of categorized these as like we really care about sine and cosine, and we really care less about tangent, cotangent, secant, cosecant. But I kind of want to readjust my lumping here and say I care mostly about sine and cosine. Next, I care about tangent kind of a lot, but not as much as sine and cosine. It's really the cotangent, the secant, and the cosecant that are the ones that I care much less about. So that's why we want to really know the tangent graph here. These ones I'm so much less worried about. You should still have you should still be able to look at that and say, oh, I know that's a secant graph right there, stuff like that. But we're going to spend half as much time on these guys right here. So these next 3 we'll kind of do relatively quick right here. So cotangent. Cotangent is just the reciprocal of tangent. Tangent sine over cosine, which means cotangent is cosine over sine. So I'm expecting them to have a ton in common. What's going to be the same? What's going to be different right here? So I'm going to say some same things are going to be, the period is still 1 pi. Our range is still negative to positive infinity. What's going to be different is that notice that our domain is different now. The tangent function said anywhere cosine is 0, we're dividing by 0, and that's no good. The cotangent function is wherever sine is 0 is where we're dividing by 0. Those are the new locations that are no good now, right? So our domain and therefore our vertical asymptotes have moved. Now, where is sine equal to 0? Well, I have no height at 0 degrees, no height at 180, no height at 360, no height at I can't even add 180 anymore right now, Friday afternoon. I'll do them in terms of pi. 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, all the integer multiples of pi, right? So x equals pi k, including k equals 0, so x equals 0. That's now an asymptote, whereas before it was the center of our tangent graph right there, right? Now, there's one last difference that we're really going to end up acknowledging here about these graphs, about this graph of tangent right here. I'm just going to kind of flop this guy out right here, is that I now know that I'm going to get a asymptote at 0. I'm going to get a asymptote at pi. Asymptote at negative pi. And I know that because that's all the places where sine is 0, and therefore cotangent would be dividing by 0. But the other thing that I'm going to see is this. If our angle is very small right here, my question is what type of stuff are we getting out? If we're getting an angle of like 1 degree right here, then what I'm seeing is that at 1 degree, right, cosine is huge. Sine is tiny. So we're getting a massive positive number divided by a tiny positive number. So we're going to get huge values. So I can see that we're going to get values that are up here when we're at like 1 degree, stuff like that. Now, similarly, once we've gone over to being near pi, right? Once we're at 179 degrees right here, I can see that we're still getting a massive cosine and a tiny sine. So we're going to get the same magnitude, but now cosine's negative and sine's positive. So I'm going to get a value that's going to be like down here. So the only thing that's really going to meaningfully change here for the cotangent graph is it goes the other direction, right? It goes top left to bottom right, whereas tangent went bottom left to top right. This one matched only because we stuck a negative on it right there, what we see for cotangent, right? So there's our good tangent graph goes bottom left to upper right. Tangent grows this way. Cotangent is going to be angled the other direction right here and shifted by 90 degrees or by pi halves, because that's exactly the difference between sine and cosine out there. Right? This should just be a lot of read. Oh wow, all three of those look different. Awesome, good job, Tony. So that's okay. We can pop back over super quick into Desmos and say, hey Desmos, what's the cotangent look like? I'll add it on the top bit right here. And so we can see they've clearly got like the exact same shapes right there, but we can now see that, for example, like the y-axis appears to actually be an asymptote. So we're getting asymptotes at 0, at pi, at 2 pi, stuff like that. Otherwise, the shape is identical, but it's a reflection and a shift is the only difference between tangent and cotangent. Otherwise, their shapes are very, very, very similar, just like sine and cosine, very, very, very similar right there. So back over here. There's cotangent, right? Secant. Given that secant is 1 over cosine of x, what features do we expect secant of x and cosine of x to have in common, and how do they differ? Well, what's going to be the same between them is that they're going to have a period of 2 pi. That's about it. But fortunately for us, there's going to be a really, really easy way for us to come up with the otherwise kind of complicated graph that we're going to get for secant and cosecant. It's going to be really easy for us to graph it as long as we think about just cosine and just sine. So here's what I'm going to do to graph this guy. Mark off a bunch of points we need. So what's cosine look like? I'm just going to graph cosine to get started right here. All right. Now, when I graph cosine, what we learned last class, remember, is that cosine of 0 is 1 because you're all width out there. So the thing that's most important to me to remember about cosine is it starts at its maximum at 1. From here, by the time we get to pi halves, we have a cosine of 0. And then by the time we get to pi, we have a cosine of negative 1. Three pi halves. We're back down to vertically downward, so we get 0. And it's going to keep on doing stuff like that, right? So let's copy this over. And here we're at negative 1, and we're at 1. So here's what I know. What I want to now draw is I now want to draw, and I'm going to draw this in a different color right here. I'm going to draw secant in green. All right, so I'll put a box in green around it right here. Here's what I know. I know that secant is just 1 divided by whatever we got out from cosine. Well, cosine of 0 is 1. So secant should be 1 divided by 1. Well, 1 divided by 1 is 1. So at that point, they're actually going to have exactly in common. Right? But now notice some other things that are going to happen over here. For example, by the time I get over here to, for cosine, as soon as we get to like pi thirds right there, cosine's value is now 1/2. 1 divided by 1/2 says how many steps of 1/2 do you have to take to get to 1? And the answer is 2. Right? So what I know is where this graph has a height of 1/2, the secant graph has a height of 2. And that's going to be the same on both sides, right? The height is 1/2 right there of cosine. So the height of secant will be 2. The next thing I can see that's really important is this. At pi halves, cosine is 0. So that means that secant is 1 divided by 0. That's an undefined value right there. We're going to end up with asymptotes, the exact same thing as we saw for the tangent graphs out there, right? We can't possibly have a value at pi half. I see that I drew that point in a slightly bad spot right there. I got to move that point over a better smidge right there. Well, maybe I did, maybe I didn't, but it's still whatever. I'll redraw here. Right? So what's going to happen is as these cosine values get tiny, we're dividing 1 divided by a tiny number. That's going to give us huge numbers that blow up. So the way that I can graph this guy is I can see that these numbers are just going to get bigger and bigger and bigger and bigger. Same over here, bigger and bigger and bigger and bigger. Now, what's going to happen as soon as we get over here, notice that we've got some sort of symmetry right here, right? These numbers are the same size as these numbers, but they're negative. So we're going to get the same types of reciprocals here. So the secant and cosecant graphs are odd. They're very strange. I shouldn't say odd because that's referring to a symmetry. But they end up having a bunch of these like loops. Oftentimes, students are tempted to describe these as parabolas, and they're definitely not parabolas because parabolas go forever left and right, and these don't. These are stuck in a vertical channel right here. These are very much more U's than parabolas that technically go, parabolas go left and right forever. These basically have vertical walls that they are never going to cross over right here. The other good news for us is that since sine and cosine have so much in common, the graphs of secant and cosecant are essentially the same in the way that the graphs of sine and cosine are essentially the same. They're just a horizontal shift relative to one another. So all the parts in green are the graph of secant. The graph that I drew in black is just cosine that I drew as my like guide function, right? So I'm going to say that right now to make sure there's no confusion here. And let's pop over to Desmos and graph them both together. And again, like literally every single time I've ever graphed like a secant or a cosecant graph in my entire life, I have drawn the sine or the cosine graph that it's partnered with first, and then just drew all my U-shapes exactly how I knew they should be. I always draw the guide function with it. So let's go graph cosine and secant together. Take a look. Here's our cosine function. Again, most important thing to remember about cosine, starts at its maximum over there. Starts at the top of the peak. Now we graph our secant function. And there it is. Hey, they even did it in green, just like me. And we get these U-shapes. But again, they're not parabolas. Parabolas do go left and right forever. These have walls. They only live for, it looks like 1 pi wide. Now notice though, these do all of our positive values 1 pi wide, and then all of our negative values 1 pi wide. So it still takes a full 2 pi to experience all possible outputs before they start repeating again. So one period of the secant function here might really look like something like negative pi halves to 3 pi halves, right? There's one full period of the secant function. It still has a period of 2 pi. That is an interval that is 2 pi wide right there, from negative a half to positive 3 halves, multiples of pi. But notice again, you got to have 2 of these disconnected lobes to have experienced all possible behavior of the secant and cosecant, or well, yeah, for secant and cosecant right here, and that still does take a full width of 1 pi wide to make that happen right there. And you know what? While we're over here, let's just swap these out for sine and cosine since they're going to be exactly the same, right? So notice that these at the peak is the minimum, and that keeps on being true. They touch at those most extreme points. Those are what they have in common because 1 over 1 is 1, so that's their one common point. So now when I switch this to sine, they don't agree right there, right? So those don't match up. But now when I change this to cosecant, they do match up again. Now notice here, this wasn't a very good interval for me to see right here. I'm going to get rid of that interval, but the point is, same type of behavior right here, right? So again, every time in my life that I've ever wanted to draw cosecant, I first drew the sine function, And then I use that sine function as my graphical guide to know how to draw the cosecant function. So, like, honestly, if I ask you to graph cosecant or secant, I'm totally fine if the graph of sine is also on there, because that's what I do. But know that these aren't, like, the graph of cosecant is just that stuff right there, right? It doesn't include the sine function. It's hard for me to draw this as a standalone function. It's really helpful for me to easily draw sine or cosine first as my guide, then to use that guide function to say, okay, I'm just going to draw these. I know that my asymptotes are at the x-intercepts, right? This x-intercept at pi, that's saying there's a vertical asymptote there because 1 divided by 0 is undefined. 1 divided by 1 is 1, which is why that's a shared point between those two graphs. Stuff like that, right? So over here for cosecant, only major difference. Is a shift by pi halves, right? So we're going to get here, same kind of style, is that we're going to get our sine graph. We know it goes through the origin here. Sine of 0 is 0. We start at the origin, and that's going to allow me to go ahead and draw my lobes right here. Again, 1 over 0 is undefined, so that's an asymptote location. So here should be my asymptote, and another one right there. Since that's a 0, that's going to be an asymptote for the reciprocal graph. And that goes right there. That's technically 1 also. And I know this is a really bad by hand drawing, but it gets all the point across right here of the parts that we're looking at. So these graphs are, in a sense, matching. They just follow the same horizontal shift as is the difference between sine and cosine. Oh my gosh, I did this stupid thing again right here. That's okay, it was barely anything. All right, here we go. I flip back over again. The only difference between sine and cosine is a horizontal shift by pi halves. Secant and cosecant are going to have exactly that same shift. Here was our secant graph. It's the reciprocal of cosine. Similarly here, I drew my graph of sine, and then in green, I just drew my lobes that come down and touch it at its peaks with, and again, my important thing is wherever sine is 0, is where cosecant is undefined, because cosecant is 1 divided by sine, so we never want to do 1 divided by 0. So that's it. So these are like relatively easy in the sense that they're not really that easy, but as long as you have your guide of sine and cosine, they kind of are. And the other good news is our transformations are still just doing the same thing for us as they used to be doing. So let's do one quick transformation right here. Help ourselves out. So I'm going to do this as like a series of transformations here to help myself. I know that if I were to plug in a number x, the order of operations would be first evaluate cosecant, then multiply by 2, then add 1. This will be kind of our last thing we do here. So what I want to do is I want to do each of the graphical transformations in that order. Right? So I'm going to start with just a cosecant graph. I know that the cosecant graph is 1 over cosine of x. So I'm going to draw, maybe I'll draw like in a dashed line right here, my cosine of x function. And that says to me that my cosecant function should be this guy here. Now I want to do 2 times cosine of x, 2 times cosecant of x. Now what I know is that this is like the same thing as saying I'm going to graph for myself. I'm now going to graph the 2 cosine function, so it's going to be twice as tall, right? So that's only at 1. I'm going to give myself more room so I can emphasize this here. So now my cosine function goes the whole dang way, right? From -2 to +2. So again, I'm using the cosine function as my guide. 2 cosecant x, you should just graph 2 cosine of x and then do your flipped parts, right? Finally, we want to add 1. So to get 2 cosecant of x, every time I write the word or the function for cosecant, I want that third c to be my parenthesis, and then I end up in the wrong spot right there. Now I'm just going to shift the whole graph up by 1. So now I'm thinking to myself, I want to draw as my dashed line 2 cosine of x plus 1. And then I'll do all of my reciprocal lobes with it, right? So I want to take this whole graph and shift it up by 1. So it used to go down to -2, it's only going down to -1. It used to go up to +2, it's now going up to +3. And now we can go ahead and, again, my guide lobes are helping me right here. My guide cosine function is guiding me here to get my lobes that are going to be on there, right? Now I know that got a little bit sloppy right here. Let's go check this guy out in Desmos and see that it's going to agree here. And I'm going to do them both together. Right? So we're going to get our cosine of x and our secant of x. Oh wait, no, we just did, wait a minute. Ah, shoot, I did my dumb thing right here. I matched these up all wrong, right? Cosecant goes with sine. So I'm just going to change this problem so that this actually agrees with what I meant for this, for what I end up drawing. So I'm rewriting this instead. It looks like we actually drew the secant function. That's the partner with the cosine right there. So let me just fix this. Friday afternoon has arrived, apparently. My brain is slightly less on it than it should be. Okay, now. Okay, I lied. Now we're doing secant because I made the mistake. Right? So cosine of x and secant of x, right? Those are the things we want to compare here. Now the first thing we did is we doubled cosine. And notice those don't agree, but now when we go ahead and we double secant as well, oh, what do you know? Oh my gosh, and for the, oh man, I am really on a roll. I'm glad we're wrapping it up right now because I have made the 18th mistake here. Okay, now that I'm on the right screen and I'm graphing the function that I mean to be graphing, we're looking at cosine of x and we're looking at secant of x. Okay, here's my starting 2 graphs. I'm going to keep them in the colors that we've been using right here. It's like my black dashed line, and this is like my green solid line or something like that right there. Right? I'll just make that. Here we go. Green's fine. So what we want to do now is say, okay, we then upgraded this to be 2 cosine of x, which doesn't agree anymore with the secant graph right there. But if we also double secant, yeah, now it does again. Now our 2 times cosine of x is our guide function for 2 secant of x. Then again, we're going to add 1 to this thing right here. It's no longer a good guide for 2 times secant of x, but if we do the add 1 right here, oh, what do you know what matches up again, right? So anytime you're trying to graph any transformations of secant or cosecant, just pretend it's not the appropriate sine or cosine, and the appropriate one, don't get them wrong like I did right there. Draw the sine or cosine graph first, and then again, you just identify where's your asymptotes, where's your maxes and mins. Draw your lobes attached to those things right there. So always use your sines and cosines to guide your secants and cosecants, and then you have to know your tangent and cotangent a little bit separately right there. So I'm going to switch back over, and I'm actually going to switch back over both for me and for you right now before I start talking. Hey, there we go. What do you know? I nailed it. So what did we do? Well, here's the 6 graphs that we are now responsible for. Right? We've got our sine graph, and again, I think my most important stuff right here. I'm going to draw some things on these, which maybe I shouldn't do, but that's okay. That's all right. I know that sine of 0 is 0, and so I remember that it goes through the origin and it's increasing through the origin. Increasing meaning it's got a positive slope through the origin. Cosine, I remember that this guy always starts at its maximum up there. That's, to me, the most important part of the cosine graph. My tangent graph, I remember that we are experiencing asymptotes and that we pass through the origin. Cotangent, I guess, is what we should do next. This guy does not go through the origin right here, right? This is going to be shifted by that pi halves relative to tangent. It is also flipped. You can think of it either vertical or horizontal, and we can identify some intercepts. Secant to cosecant, we know that we should be thinking about our related graphs that go through them right here. Right, this is our sine graph, is our guide graph, and our cosine graph is our guide graph. That's right there. So use these as our like kind of helpers. The other thing that we need to know about all of our graphs right here is that we can perform all these algebraic transformations associated with graphical transformations. We saw today that these get a little bit weird defining things in terms of like midlines and amplitudes. Those are words that are better used only with our sine and cosine functions, but in a sense they still do the horizontal shift, horizontal stretch, vertical shift. If we describe them more generically, they do apply to all 6 of our trig functions. So we know that this addition on the outside is a vertical shift term. That's what we usually use the letter K. It's our midline for all these functions, I guess, but that word is a little bit weird for everything but sine and cosine. Our amplitude is our vertical stretch factor relative to the midline of K. So we're stretching from the midline by a factor of A. And again, an amplitude is something that really is a word that only makes sense for sine and cosine, but the idea of a vertical stretch factor makes sense for any of these functions here. Our phase shift is our horizontal shift amount. Don't forget, it's got to be factored out in here. We can't just have an omega x minus phi. It has to be the factored out, like x minus phi is its own grouping right there, or else you're not really looking at the amount of the phase shift. And finally, that omega term right there. Omega isn't the period. The natural period is 2 pi if omega is just 1. We can compute the period from the omega that we see right here. By just doing 2 pi divided by that term. And the nice thing here is that if I give you the period, you can compute the appropriate omega with this formula, and the exact same formula with these 2 switches is also true. And so if I give you a formula with an omega in it, you can do 2 pi divided by the omega to get the period here. Here's the period, right? And that's good for us right there. So here's kind of all of our graph stuff. These are the 6 graphs that you're responsible for, as well as all 4 transformations potentially being applied to any of them right here. I think the easiest transformations are sine and cosine. I'd say the second easiest are secant and cosecant because you use sine and cosine as your guide graphs. I think the hardest ones to transform are excuse me, tangent and cotangent right here. I won't ask you to do crazy transformations of these guys right here, but I certainly expect all possible transformations for these 4 graphs right here. These are the more reasonable ones to do right here. So there we go. We now have the graphs of all 6 of our tangent all 6 of our tangent functions, all 6 of our trig functions. And what you know is that Desmos should be your best friend. So stick with that. The only thing I want to say to wrap it up right now is that you can see that next week what we're going to do is we're going to do our one very out of place section here, section 5.2. Technically, the trig content in this textbook starts in chapter 6, so chapter 5 is before anything started with trig. But what we want to do is we want to discuss now inverse trig functions that we can undo a trig function being applied to something. So if you have y equals sine of x, how do you solve for x? Right, that's going to be our goal in the next week here. But to do that, we really need to understand inverse functions generally, not just for trig functions, but like how do inverse functions work? How do you find the inverse of a function? What does it look like graphically? All that kind of stuff. So section 5.2 is really going to be us stepping back and spending a day on just algebra stuff. So if you've taken college algebra, then you've technically covered this. What I also know from my experience is that all of my college algebra students only remember about half of the things that I want to say about this right here. So even if you've already taken college algebra, I am confident that the probability that you already know everything you need to know about inverses is low, just based on historical probabilities. No offense. So we're going to hit 5.2, which is just going to be an algebra day. There's going to be no trig in 5.2 for our first video next week. And then 7.1 is going to be us obviously starting chapter 7, applying what we learned in 5.2 to trigonometric functions in section 7.1. And that's what we're going to get next week. So come hit me up in office hours if you have questions. I had a couple of really good office hour encounters this past week. I'm going to just help you do your homework, so there's no reason to not come to office hours if you're stuck on any of this math and math stuff here. So come hit me up if you got questions. Otherwise, I will see you guys for 5.2 and 7.1 next week. Have a good one.